Hi, my name is Jerome Staal and I'm a senior editor at Nature Medicine. Today I'm at the 87th Cold Spring Harbor Laboratory of Symposium looking at stem cells, and I'm delighted to be joined by Professor Mummery from Leiden Medical Center in Holland. Maybe as a bit of a start, I was wondering if you could give us a bit of a background about your work, what your laboratory does, and your research interests.
Yeah, so for various reasons we've been interested for a long time in the heart and vasculature. And when in 2001 it was, 14th of February, Valentine's Day, we got our first beating heart cells from human embryonic stem cells. I thought, this is it. It was so exciting to see. It was a sort of eureka moment. And we started building models for the heart from that moment, making it more efficient. And initially at that time, one justified doing human embryonic stem cell research by potential applications in repairing organs, in our case the heart. But in about 2007, 2008, I thought this is going to be a really long haul, very expensive, very difficult. So we started looking for other things to do with them, and I've been very excited about what's been coming out. For example, we can predict toxicity of particular drugs on the heart much better in our in vitro models using human cardiomyocytes from stem cells than we can in a mouse. And it's much more accurate. We're also making very nice disease models. My background's actually in physics, so it really appeals to me to be able to measure electrical behavior of cells, force of contraction, all the things we can do in the most recent stem cell models of the heart.
Fantastic. And you talk about all these features that occur within the dish, contractibility and electrophysiological. Do you see, when you take samples from, or grow tissue samples from patients, do you see similar things happening? And what ways do you address some of those issues within the dish?
Yes, so if you're asking what do we see if we take a biopsy from a human heart, well, of course they're very difficult to get, very difficult to make survive, so that's a little tricky. And you certainly can't grow the cells from them, but what you can do is translate, let's say, drug responses in a patient to what you see in the dish. In humans, in our human models, and they correlate very well. So if you would try to do the same with a mouse heart, it's very difficult. If you would look, let's say, at something we call arrhythmias, which is abnormal heartbeats, mouse heart beats at 500 times a minute, human heart at 60. So if you're looking something that increases heart rate, it's really hard to see in a mouse, or decreases it. It's not always very relevant for humans. Different ion channels, different ways of regulating. So in as far as that's been done, and as far as it's possible, then it's very, very similar.
We've seen in the field this rise of induced pluripotent stem cells, and you mentioned originally starting with human embryonic stem cells. Do you feel that the introduction and the use now of human iPS cells has changed the field, and how have you incorporated this into your work, and in what ways?
Yeah, that's an interesting question. The advantage of iPS cells, of course, is you can derive them from a patient with a genetic disease, which has made our disease modelling really very, very relevant. On the other hand, if you are looking towards using the cells for transplantation, the only advantage of iPS cells is that it could be isogenic with the patient. But in general, that's regarded as being too expensive, so very few people are doing it. And actually, this is a case, in my opinion, where, let's say, ethics has won it from safety, which is quite interesting, because the ethical reluctance to use human embryonic stem cells is very high in many countries, and the level is much lower. Let's say the resistance is much lower for iPS, yet we know the potential risk of using an iPS cell must be higher because they've been reprogrammed. So they've undergone many more manipulations in the laboratory than a human embryonic stem cell.
That's interesting.
So it's quite curious that, let's say, you could have an ethical debate on whether the ethics should win from safety in that particular case.
That raises an interesting topic. So on coming back to this idea of growing organs in addition, basically growing hearts. Is there still a drive? Is there still a drive towards the transplantation side, or do you feel the field right now is still at the understanding disease mechanism stage, or drug responses, for example?
Well, I mean, that's, you could say, kind of the low-hanging fruit. Why there's been a concentration of these disease models for arrhythmias or abnormal heart rate is because the ion channels are expressed at very early stages in heart development, which means they're present, nearly all the ion channels are present in an IPS or ES-derived cardiomyocyte. But if you look at the diseases that only develop after birth, and most heart diseases are like that, we often can't get mature enough cardiomyocytes to actually see the disease, and that's exactly what my lab works on. How do you get them to be more mature in a facile way that you can reveal a disease phenotype? Because you can't see the phenotype robustly, then you will never be able to screen for potential new drugs. Or, let's say, stratify patients. Which patients are going to respond to a very expensive drug and which not? If a drug would cost, let's say, $100,000 a year, and you give it to a patient who's not going to respond, it's a waste of money. And you see increasingly that we can predict which patients are going to respond and which not. And we can look for alternatives or combinations of drugs that you could never do in any kind of trial, possibly in animal experiments, but we already know they're not always that relevant.
Yeah. What are some of the, you mentioned the technical side of it, and you have a fantastic background in biophysics. What are some of the technical changes that you've seen that have over the years that have sort of improved on the stem cell side?
I think the improvements have been related mostly to differentiation protocols and standardization. So, of course, we still see differences in how different cell lines respond to different protocols, or to the same protocol even. But that's got a lot better, and the commercial source of many reagents, the moving away from growth factors or serum-based protocols, has made an enormous leap forward in the ability of many labs to do this kind of research, which I think is extremely exciting. And probably that technically is the most satisfying thing. So when we first made cardiomyocytes, we had about 5% in our sort of little aggregates, and most lines will produce 95% cardiomyocytes now. Okay. I mean, that's a quantum leap forward. I think also what people are working on now, including ourselves, is using artificial intelligence to predict in a very early stage of differentiation whether the differentiation is going to be successful or not.
Oh, okay.
So that means, if you can predict on day 3, this is going to be really a good differentiation, we'll go for it. Wow. It saves you time, it saves you money, it saves you reagents. Yeah. So we're getting there. And it's also helping us optimize the protocols for cell lines which don't differentiate as easily. Wow. So, when we do a differentiation protocol, we do X on day 1, and then something else on day 2, and something else on day 3. But nothing will happen if the cell's not ready for it. And you can use AI to actually predict whether the cell is ready for your factor X, factor Y. So I think that's going to make the next move forward, that it will be very efficient in many labs.
Well, that's very exciting. So, one of the main issues in the field, at least across the stem cell field, is it's enormously expensive, particularly with human stem cells. To maintain them, it takes a long time. So to have an approach that can predict would be enormously helpful. Sort of building on from that, what do you think are the major obstacles right now within your area and within stem cells in general, if you want, but particularly within your area?
I think transplantation is still a very difficult challenge. I mean, the things that are in trial now, let's say for macular degeneration, perhaps for diabetes, perhaps for other diseases of the eye, various things that are moving into the clinic are going pretty well. Okay. But essentially, it's rather the low-hanging fruit in the sense that there's relatively few cells needed. It's usually only one cell type that's affected. Let's think of Parkinson, the dopamine-producing neurons. It's only one cell type that's affected, so you just replace one cell type. And if it's functional, you could say problem solved. But if it gets to really difficult things like, let's say, muscular dystrophy, or it gets to lung diseases, it will be much more difficult, and even the heart's going to be really difficult. So those are the major obstacles to using cells as a therapy. But what we're seeing at this meeting, for example, or many meetings, is that making models that are simple enough to use but complex enough to capture the phenotype you need, so doing as a basis for phenotypic screens, is really exciting. And the question is really how we do the readouts. What are we going to read out? How are we knowing whether a cell is sick or not? And the other thing is, how do we get the difference between baseline controls and the disease big enough to actually do a screen?
That's right. Yeah.
If it's only a factor 2 and I'm looking for a dose response curve, it's not going to happen. You need a factor 10.
Yeah.
And there's actually been a recent analysis of even papers in top journals, and it turns out that many of them are actually underpowered. And we very often don't do a power analysis necessary to make the outcome robust for the difference in the controls and the disease. Whereas clinicians, they know exactly how many patients they have to include to get an outcome.
That's right.
And it's still quite rare to do that for iPS cells. Some people do it, but it's something the journal should think about. Is this properly powered?
Well, I'm so sorry we're running out of time, but thank you so much for meeting with us, and look forward to hearing a bit more about your work in the future.
Most welcome. Thank you.